some like pros or cons about using it, and then we'll see how we can use it in scikit-learn. Okay, so first, let's start with the intuition on how the algorithm works. So say we have two classes of points here, right? The red circles and the blue squares. And we have this star, which is a point for which we want to predict a class, right? And the idea here is to use the information of the closest data points to like predict what's going to be the label for that star, right? So the question here is that we need to select how many of these close points do we want to use the information from, and then we will also need to define like how do we define what is a close point, okay? But then using your intuition on like what is something being close to another thing, and say that you want to use the three nearest neighbors of the star, which class would you predict for this star? B, yeah, because like from the nearest neighbors, when the number of nearest neighbors is 3, we have 2 circles there. If instead we were to use 7 nearest neighbors, which class would it be? Yeah, because in that case we would have more neighbors of the A class. Okay, so this is already an intuition for one of the problems of the algorithm, or one of the things we'll have to solve. Okay, so this was an example on how to use the k-nearest neighbors in a classification problem. Now we're going to see how we can use it in a regression problem. The intuition is again the same. So we have these points which are in a 2-dimensional space, right? For each point we have an x coordinate and a y coordinate. And for the star, we want to predict, so we know the x value of the star and we want to predict its y value, okay? So again, if we want to use the three nearest neighbors of the star, those will be the points in that gray area, right? And in this case, there's no such thing as like the most frequent, right? So we can use the average of the y values of the nearest points and predict that value for the star. So can you roughly tell in this case what would be the predicted y value for the star? Yes, so we have one neighbor here which has 2, another here that has 4, another here that has 5. So if you take the average of that, yeah, somebody did the computations. Yeah, is this more or less clear, the idea? Okay, cool. Again, we could use a different number of neighbors, right? So say k equals 5, where k is the number of nearest neighbors, and in that case we would also, I don't know, Manu, you tell me the average of 2, 4, and 5. Oh, thank you, 3.875. Okay. Yeah. Okay. Good thing to do afterwards. Right. So we figured out how could we compute both class labels or like y values in a regression problem using the k-nearest neighbors. But now we need a very important thing, which is to define how do we actually figure out what are the closest neighbors, right? So yeah, for that we need to know what's a distance measure. Let's first start by talking about Euclidean distance. This is the distance that like you all know if you went through like normal school. So yeah, sorry. Yeah, exactly. I did that one. Sorry. Okay, yeah. So in the Euclidean distance, say in this case we have 2 points, point P and point. Oh, there's a typo there. Sorry. Yeah, we have a point P and a point Q, and what we need to do is just subtract the values in one dimension and square it. Subtract the values in the other dimension and square it, and then sum it and take the square root. We can like bring these 2 more dimensions, right? You just keep those sums coming over all the dimensions, and yeah, we can compute the Euclidean distance with more dimensions. Okay, so this is very intuitive, right? It's as if we were to use a ruler to measure the distance between 2 points in real life, but there's other ways to do it. So we could use the dot product to also measure a distance. This is like the formula to compute the dot product between 2 vectors, but it doesn't give us an intuition on like how can this be used to see if two points are close together or not. So let's help with an image. So say we have this vector u and we have this vector v. What the dot product is measuring here is measuring the product of the norms of the two vectors, but it's weighted by the cosine, which is a measure on how much these two vectors are pointing towards the same direction. Okay, so in the case where these two vectors are pointing exactly towards the same direction, we get the maximum value of the dot product, which is going to be like the norms of the two vectors multiplied. In the case where the two vectors are perpendicular, does anybody know the value of the dot product in this case? Yeah, it's 0 because they're pointing towards different directions. So yeah, we don't we get that they're not similar at all, right? Yeah, then we have a problem here with the dot product, which is that we're still like considering a lot the norms of the vectors. So imagine that we had one vector which is really long, and the other vector which is really small, and they're actually pointing towards the same direction. But then what would happen would be that that number would be small because the product between the two norms would be like small, since one of the numbers was very small, right? So if we want to be agnostic to the sizes of the vectors, and if we just want to be concerned about if they're pointing towards the same direction or not, we can use the cosine distance, which is basically taking the cosine and then do 1 minus the cosine, okay? And the interpretation of this is like a measure on how much two vectors are pointing towards the same direction. So yeah, a quick recap on what we saw. We have the Euclidean distance, which like measures a physical distance as we're used to it. The dot product measures how much two vectors are pointing in the same direction, but then we care about the vector's norm. The cosine distance just cares about if they're pointing in the same direction or not. And then I put this small note here because I wanted to like just note that the dot product and the cosine distance, they're not actually distance functions, because they don't respect the triangle inequality. Yeah, but this is more like for Ugo not to bother me afterwards because he knows all about maths. Yeah, but like in this context, let's use these all three. We can call them distances. Nobody will care. Yeah. Now considerations about kNN. If you paid close attention to how the algorithm actually works, you probably like noticed a difference between this and say linear regression that we saw yesterday. So in this case, we weren't doing any assumptions on how like the model would be structured, right? If you remember yesterday when we were using linear regression, we were making the assumption that the data were somehow like placed in a linear way, okay? And in this case, we're not doing any of those assumptions. So the model will end up predicting whatever the data is showing it, okay? So it's, okay, yeah?
For example, if you have somehow sparse data.
Mm-hmm. We'll go into that.
Maybe the k-nearest points are not so
we'll get there.
Okay.
Yeah. Okay, so the first observation is this one. It's a non-parametric model because it's not making any assumptions on the data. It's learning whatever the data is showing it. And as you can imagine, like the more data you show it, the better your predictions will be, right? Then second consideration, we're not doing any learnings here. We're not, yeah, you remember in linear regression, we were interested in learning those coefficients, right? And then based on coefficients that we would learn on a data set, we would try to apply that model in unseen data. And it's as if like somebody was learning from the first data set and applying knowledge on new predictions, right? In this case, we're not learning parameters. All we're doing is just like taking data in, comparing the point for which we want to make a prediction, use the data that is close by and build a prediction based on that. So if we use the different data set, we would probably get different predictions. It's not like called learning.
What about the number of nearest neighbors?
Exactly. So the number of nearest neighbors, it's not a parameter of the model, it's an hyperparameter. For instance, when we saw the C parameter from support vector machines, That's an hyperparameter. It's something that we want to find what's the best value to solve the problem that we have in hand, but it's not something that we will learn. Okay. Yeah. Yeah, we will need that. I'll explain it later, but it's like the idea is like first we will need to figure out what's the best value for k. Yeah, and that's something called hyperparameter tuning, which we'll like cover later. And then it's always a good practice to check if your model performs well on unseen data, right? Yeah, but like that's it. We're not learning parameters here. We're just like using data to see if it works. Yeah, there you go. K needs to be tuned. Some consideration here, which is like if we use more neighbors to get our predictions, we will have less noise, so we'll be less sensitive to noise. But then if we start using a too large k, we'll start making bad predictions because eventually we'll just take like the average or the most common value among everything in the data set, which doesn't make sense, right? Yeah, and we'll later learn how to do this tuning of this k parameter in a systematic way. Yeah. So from what you were saying, there's a tiny problem here. So if you see these three images here at the bottom, the first image shows you how like points are distributed if they can only be spanning one dimension. Okay, you see there. In the second one, we're allowing the points to spread across a second dimension. And one thing that we can see here is that like in the second image, they have much more like room to spread, right? And if we add an even third dimension, they even have more space to be spreading, right? So as we keep adding more and more dimensions, the data starts getting more and more sparse. And what does this mean? Means that like in a probabilistic way, if you get a point and you try to find what's the distance at which the k nearest neighbors are at, those k nearest neighbors won't be much closer than any random other point, right? So in that case, you cannot really make good predictions. So yeah, we break the assumption that the points which are similar, which are closer to one point, are more similar to it. Okay, there's no like relationship between points. Yeah, one good way to take care of this is to use, for instance, the cosine distance instead of the Euclidean distance, because it's a bit better just to be measuring like orientation instead of actual distances. Yeah, but this is something that you always need to be concerned about when using this algorithm. And then another consideration is, so we've described how could we build predictions for 1 point, right? But if you want to build predictions for 1,000 points, eventually you're going to have to compute distances between each of those points and all the points that you have in the data set. So this doesn't scale very well. There's ways to make this more efficient, right? But first you need the distance function to actually be a distance function. So you could, yeah, like scikit has some optimizations out of the box, but you can only use them with the Euclidean distance. Yeah, and there's other methods to do it, but then the algorithm is not so simple anymore. It starts being more complex. Yeah, and there, which is more or less some, sorry. So other than the approximations, if you're allowed to like simplify your problem and not use the exact k closest neighbors, but k neighbors that are close enough, you can do an approximate nearest neighbor search, which will be like more efficient, but will probably not get you the result correct 100% of the times. Yeah, so if we've all like understood how does this work more or less, if we want to use this algorithm in scikit-learn, we can either use it for classification or regression by just importing either the classifier or the regressor, right? Oh no, I pasted the same cell twice. Sorry. Yeah, I'll quickly fix this. But basically, the idea is just like you need to import it, and then you just instantiate the class with the number of neighbors that you want to use, and then you just call like a fit and a predict as you would. But basically, what's happening in this prediction phase is just that you're using your training data to compute those distances. Okay, so yeah, in this case, the training, it's still called like fit and predict, but in the fit you're not doing much more than just memorizing all the points that you have in the training data. Yeah. Yeah, so recap is like kNN is very simple. We can use it for classification, regression, and other types of problems. We need to be careful when choosing the distance function. Yeah, like the plain version has some caveats, which is it can get quite slow, and we have the curse of dimensionality problem. Yeah, but it's the basis of algorithms which are used like in real life, which is pretty cool when you understand how this works. Yeah, that's it. If you have any questions.